Welcome to another topic in material science and engineering. Today, I will be discussing destructive material testing, topic number 3. Why are metals tested? Maybe this is also one of your questions. Metals are tested first to ensure quality. Before we can use metal for a particular application, especially for a very critical or sensitive application that requires a certain property or quality, we test metals to ensure that it is able to give the specific requirement or to attain the specific requirement for that particular application. The second is to test the properties. So some engineers test metal to know whether it attained a particular property based, for example, on the manufacturer's data, or also to verify information about the property of a certain metal. Third is to prevent failure in the use of metal. Just like what I said, there are certain criteria that will be required for a particular metal. That is why safety is very important, especially in the finished product. So that's why it is important to prevent failure when using this particular metal, and to make informed choices in using materials. Just like what we discussed before, one of the primary uh, importance of materials science and engineering is to be able to select the proper material for a particular application. So material testing will help us also have an informed choices in selecting the kind of material that we will use. We have this term we call factor of safety, which is the ratio comparing the actual stress on a material and the safe usable stresses. So in machine design, we will encounter factor of safety, and we'll be able to understand why it is important to have a certain allowances that will help us decide what kind of property is needed or allowed for a particular application. There are two forms of testing. The first one is called the mechanical test. This is also called destructive testing, where it requires destroying the specimen in order to measure the property. So here, we will get the property, but we will have to destroy the material in question. And it requires a specifically or specially prepared specimen. So some example of mechanical test is your tensile test, your compression test, wherein you're going to uh, have the material being compressed or being stretched so that we can identify the different properties. And then we also have the second classification, the non-destructive test, which measures attributes of the specimen without damaging it. It does not normally need a prepared specimen, just like the mechanical testing. Some example are your ultrasonic test, radiographic testing. We also have X-ray testing, all of this which does not necessarily destroy the material in order to get the property that we are looking for. So non-destructive tests are typically used to find flaws inside a material part. Say for example, you wanted to know whether there are discontinuity or there are holes in the metals or there are cracks, then we can use non-destructive tests to verify whether these flaws are present. Because the identification of this flaw will help us also to avoid failure later on, because eventually when this material is being applied, these flaws will eventually grow and may also cause failure in the particular application. So in this table from Lembo CMMS, we can see the difference between destructive testing and non-destructive testing. So we can see that in destructive testing, the tested specimen get deformed or damaged during the testing process, while in the non-destructive test, the tested specimen does not get damaged during the testing process. For destructive testing, it is done to identify chemical and physical properties of the tested items, while non-destructive test is carried out to find the defects or the flaws in the material. Your destructive testing is extremely useful for design purposes, while your non-destructive test is great for spotting early deterioration signs of working equipment. Also, for destructive testing, the tested item cannot be used for its intended purpose, while for non-destructive test, the item can be used in normal operation after testing, if it is not found to be defective, of course. And for destructive testing, it is more expensive and time-consuming, while non-destructive test is quick and easy, even though certain testing equipment can be fairly expensive. Examples of destructive testing are bending test, tensile testing, hardness test, corrosion testing, and compression testing. Examples of non-destructive testing are ultrasonic testing, radiography testing, vibration analysis, and magnetic particle testing. By the end of this lesson on the non-destructive material testing, you should be able to differentiate destructive and non-destructive testing, list the various destructive testing of materials, describe the procedures on destructive material testing, enumerate the mechanical properties obtained from destructive testing, and explain the importance of material testing in our practice in mechanical engineering. So the focus of this discussion will be on the destructive testing. So in this outline, we can see the different non-destructive tests, destructive tests that will be discussed. Starting with the general test, which is the mechanical test. So again, mechanical properties are relevant for engineering. Some examples are shown here in the table, like strength, stiffness, hardness, and toughness. We can also see in the table the different tests, mechanical tests, or destructive tests that can be done in order to measure these properties. For example, for strength, we can use tensile, compression, or shear test. For stiffness, we can have the slope of the stress strain curve developed from the tensile test. Hardness test can be done using the Rockwell-Brenner and Vickers test. Toughness can be done using impact test through Sharpie or ISO testing. Some properties can be measured easily, like hardness. Others may require breaking a specimen, like the measurement of the ultimate tensile strength. So now that we know what mechanical testing is, let's dig deeper to the specific mechanical testing, starting with the hardness testing. So what is hardness test? Hardness is the ability to withstand indentation or scratches, as you can recall in our previous lesson on the nature and characteristics of materials. It is also the resistance to indentation or abrasion. As you can recall, we have what we call the Mohs hardness scale, which is one of the scale in describing hardness. So in this illustration here, for example, you can see the increasing hardness, wherein diamond in this chart is the hardest of all of these stones being depicted here in this photo. So in hardness testing machine, the indenter is pressed into the metal. So softer materials leave a deeper indentation. So you can see here the illustration of a hardness testing machine. So we can find here also the position of the indenter. So this indenter is pushed into the metal that you are testing. So we have here the item for test. We place that material here, and we can adjust this nut here in order to achieve also the level of test that you'd like to achieve. So most machines in use are almost fully automatic and can carry out various hardness tests. So this machine can carry out the different hardness tests that will be discussed later on. So you can see here the actual photo of a hardness testing machine. So you can also see here the measurement scale that will help us identify or measure the scale or the rating. We can read the result right there. So this is a smaller version of the hardness testing machine. So one example of hardness test is the Brinell hardness test. So there are different classification or ways to test hardness, and the first is the Brinell hardness test. So this uses a ball-shaped indentor, and it cannot be used for thin materials. The ball may be deformed on a very hard materials. The surface area of indentation is measured. So you can see here the hardened steel or tungsten carbide ball that's used for Brinell hardness test. So the diameter can be 1 mm, 5 mm, or 10 mm. So this is the indentor for the Brinell hardness test. For Vickers hardness test, it uses a square-shaped pyramid indentor. So it has an accurate results and measures length of diagonal on indentation, and is usually used on very hard materials. So you can see here how the indentor looks like. So it is a square-shaped pyramid indentor, as you can see here. So for Brinell, we have a ball-shaped indentor. For Vickers, we have a square shape. For Rockwell hardness test, it gives us a direct reading. The Rockwell B ball used for soft materials, while Rockwell C, the cone type, is used for diamond cone for hard materials. It's flexible, quick, and easy to use. So you have here some of the images of the indentor used for Rockwell hardness tests. Now that we know the hardness testing, let's proceed to toughness testing. So what is toughness? So toughness test is also called impact test, where it measures the toughness of metals. The toughness of the metal is the ability to withstand impact or the energy before it break. So you can see here the image of the machine or equipment that is used for toughness or impact test. Two classifications are described here. We have the ISOD impact test. So here it strikes the material at 167 joules, and the test specimen is held vertically. The notches faces the striker. So you can see here how the ISOD test is being carried out. So this is how specimen is held for carrying out an ISOD test. So we have here a notch. So we actually have to create this notch where it faces the striker. And this is our test specimen. So this is where the striker strikes this test specimen. So the test specimen is in a vertical position, as you can see here. That's for ISOD impact test. And we also have the Charpy impact test, where the strikers form higher position with 300 joules. The test specimen is held horizontally as compared to ISO test, where the test specimen is held vertically. The notch faces away from the striker. This is also opposite to the ISO test. So you can see here our specimen is now positioned horizontally, and our notch is faced away from the striker, so it's in the opposite side. So that's the difference between the ISOD impact test and the Charpy impact test. But more or less, the principle is the same. We have the striker striking the test specimen at a vertical or a horizontal position, whether the notch faces away or uh, directly faces the striker. So again, it measures the toughness of the material or its ability to withstand breaking. So let's proceed to tensile testing. So what is tensile test? Tensile testing uses an extensometer to apply measured force to a test specimen. So the amount of extension can be measured and graphed. The variables such as strain, stress, elasticity, tensile strength, ductility, and shear strength can be measured using tensile test. The test specimens can be round or flat. In tensile test, the tensile loads are those that tend to pull the specimen apart, putting the specimen in tension. They can be performed on any specimen of known cross-sectional area and gauge length to which a uniform tensile load can be applied. Tensile tests are used to determine the mechanical behavior of materials under static, axial test, or stretch loading. So this is how our extensometer or our tensile testing machine looks like. And we have here an example of a tensile test specimen. So in a tensile test specimen, we have what we call this gauge length. Then we have the cross-sectional area of the uh, test specimen. So the test specimen can be flat or round piece. You can also see here the cap and cone fracture, which signifies a ductile material. A shear fracture would indicate that the material is a brittle material. We can also find here the types of extension under the stress strain curve. We have the elastic extension, the plastic or ductile extension, and the necking range during the tensile testing. So the elastic extension is a portion of our graph wherein the the load and the extension are directly proportional to each other. And then we have here the plastic or ductile extension and the part where the test specimen undergoes the necking before it finally break. So this is the stress strain curve that we also discussed in the nature and characteristics of engineering materials in topic number 2. So we can divide that in the different region, the elastic region, the yielding region, the strain hardening, and the necking region. So this is how the necking and the tensile specimen looks like. So as you can see here, we can find an elongation at the middle part. So this is how it looks like, especially for ductile material when it undergoes necking. For brittle materials, it doesn't undergo necking. It will automatically break. You can also find here the different stress strain diagram for the different materials, having different kinds of properties, whether it has high strength, low ductility, and low toughness. This is how the graph would look like. If it has high strength, high ductility, and high toughness, the stress strain curve would look like this. If it has a low strength, high ductility, and low toughness, this is how our stress strain curve looks like. So by the look in the stress strain curve, we can already identify the property, the mechanical property of the material. The mechanical properties that can be measured using the tensile test are the ultimate tensile strength, which is the maximum tensile stress that the material is capable of developing during a test. We also have the load, which is the force applied, either pounds or newtons. The stress is the intensity of the internally distributed forces or components of force that resist a change in the form of the body. So the three basic types of stress are tension, compression, and shear stresses. The elastic limit, on the other hand, is the greatest amount of stress a material can develop without taking a permanent set. The percent elongation is the total percent strain that a specimen develops during the testing. Let's proceed to compression testing. Compression testing is actually just the opposite of the tensile test. So instead of pulling the test specimen, in the compression testing, we are going to crush or compress the material being tested in order to measure the mechanical properties. The compression testing is just the opposite of tensile testing. A compressive load tends to squeeze or compact the specimen. So the choice of the compression test over the other types of testing depends on the type of loading the material will see during the application or service. So if the engineer already determined that this kind of material will undergo tension, then we will use tensile testing. So if it is expected that the material will undergo compression, then we will have to subject the material to compression testing. Metals and many plastics, for example, are more efficient and resisting tensile loads. Therefore, they are more commonly tested using tensile loading, depending on the application. Materials such as concrete, brick, and ceramic products are more often used in applications for their compressive loading properties and are therefore tested in compression. Because, for example, these concrete bricks, they will carry the weight, for example, of the roofing or the upper portions of the building, so they have to withstand that compressive or crushing load. During a typical compression test, the data are collected regarding the applied load, resultant deformation or deflection, and the condition of the specimen. So for brittle materials, the compressive strength is relatively easy to obtain, showing marked failure. For ductile materials, the compressive strength is generally based on an arbitrary deformation value. Ductile materials do not exhibit the sudden fractures that brittle materials present. They tend to buckle and barrel out. So this is what we mean by the barreling or bulging of a sample under compressive loads. So when you compress the material, it will have this barreling or bulging. So we also have what we call this Dist testing. So the Dist testing is the compression test that is developed for brittle materials like ceramics and glass. So this is a specific test for compression testing, especially for brittle materials. A disc-shaped specimen is loaded between two solid platens. Tensile trusses build up perpendicular to the center line along the disc. Fracture begins and the disc will split vertically. Care should be taken to ensure that the axis of the specimen is centered and aligned with the axis of loading. Now that we understand what compression testing is, let's move forward to shear testing. So what is shear testing? So there are some applications of material wherein it will be uh, undergoing shearing, just like what you can see here in the illustration, especially in the bolt and nut application, for example. So we have to test whether the material can withstand that shear stresses. So shear testing involves an applied force or load that acts in a direction parallel to the plane in which the load is applied. Shear loads act differently than, say, tensile or compressive loads. So these tensile or compressive loads act normal or perpendicular to the axis of the loading, whereas for shear loads, it acts parallel. Direct shear and torsional shear are important forces used to determine shear properties. So direct or torsional loading depends on the forces a material is expected to be subjected during a service. Before testing, the specimen is accurately measured using proper instruments and the gauge length is marked. The taphometer or a suitable replacement is attached to the specimen and zeroed out. Proper precautions should be taken to center the specimen in the machine or fixture. The grippers are tightened to ensure against slippage, yet not so tight as to cause deformation, which would affect the test results. This is the transverse shear test fixtures for single shear and for double shear. So in relation to shear testing is what we call the torsion testing. So in addition to tension and compression, a workpiece may be subjected to shear strains. Torsion test is used for determination of the properties in shear. So in the specific test for shear is the torsion test. It's usually performed on a thin tubular specimen. The ratio of the shear stress to the shear strain in the elastic range is known as the shear modulus or the modulus of rigidity. The angle of twist to fracture in the torsion of solid round bars and elevated temperature can help estimate forgeability of the metals. Finally, we have the bending test. So what is bending testing? So if you can recall, bending is usually being experienced by materials in applications like beams and all of these similar applications. Preparing specimen from brittle materials such as ceramics and carbides is difficult because of problems in shaping and machining them to certain dimension. The most common test for brittle material is the bend or flexure test. Rectangular specimen supported at its ends, the load is applied vertically at 1 or 2 points. The stress at fracture in bending is known as the modulus of rupture, flexural strength, or the transverse rupture strength. So you can see in the various tests the different methods and also the different mechanical properties that can be obtained. So by now you can already answer some of these questions to check your understanding. So what is the difference between destructive and undestructive testing? What are the various destructive testing that we discuss in this lesson? What are the mechanical properties that can be obtained from each destructive test? Why is material testing important in the practice of mechanical engineering? So in this lesson, we were able to discuss mechanical testing and the different types of mechanical testing like hardness, toughness, tensile, compression, shear, and bending test.